All right, so our problem for today, we are looking at longest consecutive sequence. This is actually the last in our arrays and hashing content. We're going to move on to two pointer, not tomorrow, but Monday. It's actually still arrays, so like we're still doing arrays. um, but yeah, last one for this section, and then it kind of like most of the new topics, they get easier at the start. So if you've kind of been feeling like, man, these are getting tougher and I'm confused, jump in on Monday and I think you'll have a great time. Okay, anyways, let's take a look. So our problem today, it says given an array of integers nums, we want to return the length of the longest consecutive sequence of elements that can be formed. And as you can see here, nums is a list of integers. So when we talk about a consecutive sequence, we're talking about a sequence of elements in which each element is exactly one greater than the previous element. And they clarify the elements do not have to be consecutive in the original array. So we're not talking about consecutive as in next to each other in the array. We're just talking about consecutive in terms of the values being neighbors to each other. Okay, so the example here, they give us this array 2, 24, 10, 3, 4, 5. And the output is 4 because if you were to go through all of the like neighborhoods or like neighbor groups in this array, you'd have 2, 3, 4, 5, you'd have 10, which doesn't have any neighbors, and you'd have 20, which doesn't have any neighbors. Notice that 4 is duplicated, but we don't get to use it twice. So in this case, the longest consecutive sequence is just 2, 3, 4, 5. And that means we return 4 because that's how many numbers are in that group. Okay, next one here, we've got 0, 3, 2, 5, 4, 6, 1, 1. And if you were to look through these, you could count 0, 1, 2, 3, 4, 5, and 6, which is 7 elements long. It's actually the only group here, and so we return the length of that group, which is 7. Okay, some constraints they give us. The length of this nums array is going to be between 0 and 1,000. I don't know what's going on with my throat today. So we'll have between 0 and 1,000 numbers, and the numbers themselves will be between negative 10 to the ninth and positive 10 to the ninth. As usual, that is not really something we have to worry about. We're going to assume that numbers like behave nicely for most of these problems. Great. So let's, as usual, do a little bit of diagramming, and then we'll jump back and optimize a little bit. Okay, we'll actually use their array here. So I'm going to copy this over real quick. Okay, so we've got this array 2, 24, 10, 3, 4, 5. Okay, so why are you trying to do this on an iPad? Because you gotta, how else am I gonna draw things? I don't have a whiteboard in my room like you, Dave. Well, not in my room, but anyways. Okay. So 2, 24, 10, 3, 4, 5. We'll actually get rid of the code part of this real quick. So if we wanted to figure out the lengths of the longest sequences here, there's a couple things for us to consider. Well, let's start with this. We've been told that the array is not necessarily sorted. If the array was sorted, wow, my voice is just, one moment. Okay, hopefully that lasts us the rest of the session. Okay, so if this was a sorted array, it would be fairly trivial, right? So if this was 2, 3, 4, 5, or 2, 3, 4, 4, 5, 10, 20, we would just keep going till we stopped getting neighbors. If we found duplicates, we would just not count them, right? And then we would just count up the groups. The problem with this, and this is actually something we touched on in our GBM, is searching through the array is pretty expensive. At the worst case, we might have to look through all of the array elements just to find one element, right? There's not a good way for us to predict that because it's not sorted. So if we're looking at, for example, 2, and we say, hey, like how many neighbors are in this array? Or how many neighbors does this element have? Well, we would have to look through each other element. And really, we would start here. So if the index is the same, that's not a neighbor. And also it's not because it's the same number. But we go, hey, are you my neighbor? Are you my neighbor? Are you my neighbor? Are you my neighbor? Right. And so when we have to do this every single time, very expensive, right? Not to mention, so like we would say, hey, yeah, 2 is a neighbor of 3. Okay, so that's 2 elements. Okay, is there a 4 present? Okay, yes, there is. Is there a 5 present? Yes, there is. So we just happen to get it pretty early on in the naive approach here, but cycle the numbers around and all of a sudden that isn't the case anymore, right? Here's the other problem. We just got lucky with getting the minimum element first there, but eventually when we start looking at later elements like this one, we're going to redo a part of that problem, right? We're going to say, hey, is 2 a neighbor to 3? Yes, it is. Now, is 4 a neighbor to 2 or 3? Yes, it is. Is 5 a neighbor to 4? Yes, it is. So we're resolving a section of the problem. We're doing kind of wasted work. We'd rather not do that if we can. And another thing, I'm actually going to mention a few like weaknesses of the approach and just things that we have to address in our final solution. We've got to look in both directions, right? So we need some way to encapsulate like, well, maybe we're not looking at the lowest possible element of this neighborhood right now, right? In which case we need to look to the left for smaller numbers and we need to look to the right for bigger numbers. So there's that issue. And then here's like the other half of this. Like I mentioned, we have all these duplicated subproblems. One way we could handle the subproblem issue is we could say, hey, actually, once I find a neighbor, let me go ahead and remove it from the array. But once again, if we're working with arrays and we want to delete a certain element, like if we start by looking at 2, well, actually, yeah, if we start by looking at 2, for arrays, if we want to delete this element, it's not like it just disappears. Instead, we've got to say, okay, I'm going to get rid of you, and then everything needs to move over by 1, right? So deleting from the array is also pretty expensive. We'd rather avoid it if we can do that. Okay, so let me think about this actually. I don't think I've ever coded the naive solution for this one, so maybe we will just like tackle it real quick and just really not worry about making it efficient. Yeah, in fact, we won't even deal with the deletion. We'll just say, let's see if we can code it. Okay, so here's what we could do for the naive solution. We could say for num and nums, so we won't deal with deletions. We'll just say, we'll also have a max length variable here. So for each num and nums, in fact, I can't even do that because we've got to do like, we've got to compare the index. Well, we don't have to compare the indexes. Yeah, we're just going to make this a really bad solution. You guys ready for this? We're going to say for num and nums, and then we're going to say for other in nums. So this is going to let us cycle through the entire list of numbers. So compare this element against every element of the array. Hold on. Wow, this is surprisingly difficult to code because our thing that we're looking for is gonna like change every time we like have a success, right? Maybe I'll say like target equals num plus 1. And then I'll say while target, oh geez. Yeah, we'll just make this extra bad. While target in nums. Okay, so this right here is this target in nums. This is a search statement, right? So this is once again O of n. Like we might potentially have to look through every single element of the array to successfully determine if the target is in nums. Okay, so if the target is in nums, then the neighborhood we're looking at, wow, this is a lot. Current length is 1. So like when we're looking at a specific element, like when we're looking at 2, that's at least a group of 1. So if there is an element, then the max length is at least 1, right? Okay, now look through the whole array and see if you see its neighbor, 3, right? If you do, the neighborhood is now 1 bigger. Okay, So if you do find the target, current len increases by 1, and the target also increases by 1. Thanks, guys. Okay, and then we keep doing this until we no longer find the target we're looking for. So in this case, we find 3, we increase the length by 1, we increase the target by 1. We find 4, increase the length by 1, increase the target by 1. We find 5, and then we don't find 6, and that tells us that we're at the end of the group. Okay. At this point, we can say if the current length is greater than the max length, then set max length to the current length. Okay, and then when we're done, we'll return the max length. Oh, you guys can hear me, right? Can everybody else hear me? Okay. As it often is, Dave. It is a you problem. So often. Just kidding. No, I think I'm coming through for everybody else. Did you think I was just sitting here not saying anything, typing things on my screen? Oh dear. Okay. Well, I hope. Oh, y'all want a little more typing? Okay, music to my dog ears. Okay, let's keep on going here. So this does it. Let's just make sure this works so that we can talk about the time complexity a little bit. Okay, so it does work. It's very slow. Let's talk about the time complexity of this overall. So we look through each element of the array, right? So this is O of n by itself. This stuff is kind of computationally free, but then we have to determine if the next neighbor is in nums. So that's n again, and maybe we have to do that for every single one. And since we keep increasing the target by 1, this is like, maybe we have to repeat this n times every time the target increases, right? So this is coming up on n cubed, I believe. It's pretty gross. Or no, wait, is it? No, it's just n squared with like a potentially really big coefficient on it. Because for each of these, we don't have to compare the target against n other numbers. We just maybe have to look through the array like 5 times or 10 times or 100 times, right? So anyways, it's like potentially big coefficient n squared. And then the other thing is the way that we have it set up right now, which is very naive, is when we find a target, we don't get rid of it, right? So not only are we going to find 2, 3, 4, 5, we're also going to find 3, 4, 5, and 4, 5, and 5, right? So many things wrong with this. Again, we could modify this and start using deletion operations, but for arrays, that's also very slow. So it's not going to boost our performance by very much. Okay, so what's the alternative here? Well, like we've been talking about, some of the things that are really greatly slowing us down here are searching. So seeing if we have a certain element in the data structure, potentially deletion, right, because of this whole subproblem issue. And you may recall, again, from our GBM, and if you weren't there, the slides are up, and I think the recording will be up today. Determining membership of an element and deletion are both O of 1 for hash sets. So maybe we should use a hash set. Oh, I'm glad you got your sound working, Dave. So we'll tackle this with a hash set. So what exactly would that look like? Well, first of all, again, so a little recap on hash sets. If we were to make a set out of this list, first of all, hash sets don't allow duplicates. So we wouldn't see the double 4s here. We would just see 2, 20, 4, 10, 3, 5. And again, the strength of using hashing data structures is we can determine whether or not an element is in the set very quickly in constant time, right? So when we're looking at 2, we can very quickly say, hey, is 3 in the set? Okay, if it is, do whatever, and then we can say is 4 in the set. We get that answer very quickly. Instead of having to search through every single thing, we can, or the power of the data structure is it immediately allows us to identify whether or not something is a member. Okay, and then to resolve this subproblem issue, we can say, hey, now that we have found a neighborhood group, we don't need to reconsider those members. Like if we do 2, 3, 4, 5, as long as we get the whole neighborhood, we don't need to go back and do 3, 4, 5, and 4, 5, and 5, right? So as long as we can guarantee that we kind of tackle the whole neighborhood, we don't need to repeat the subproblems. Now, that there is, like I said that very fleetingly, but that actually is something we'll have to address very seriously, is how do we make sure that we can tackle a whole neighborhood at once? Because in this case, we are looking at the minimum element, but let's say it looked like this. If we start with 4, we don't want to just get rid of 4 and 5 because that's not actually a neighborhood group. 2, 3, 4, 5 is the neighborhood group, right? So what we'll want to do is make sure that we kind of travel the whole neighborhood in both directions. So it's very easy to figure out if we have a left neighbor because you just do the number -1 until you don't find a neighbor on that side. And it's very easy to do the right side of the neighborhood because you just keep adding 1 to your target until you don't find the thing you're looking for. So we'll have to get through the whole neighborhood at once, but that's pretty manageable. So just to outline kind of the process here, we'll look through the set. We'll take just any random element and say, hey, let's go through all of the possible left neighbors until we don't find one. Okay, so like on iteration 1, for example, we would maybe grab 4. Well, you know what? Sets are not ordered, right? So, well, there are set operations that let you like grab like an arbitrary element, and specifically that's pop. So we would use set.pop, which we'll do in the code in a sec. But let's just say it's random. I've got to pick just some random one, and maybe I pick 20. So on this iteration here, we would have 20 is the number we're looking for right now, and it's got a length of 1 since we have just the one element. And we would ask ourselves, okay, is 19 somewhere in this set? No, it's not, so we know we're done with the left side. And then we would ask ourselves, is 21 in the set? No, it's not, so this neighborhood is just one element, and it's just 20. This only works with numbers and letters if you map them, not with strings. Well, you would just need some notion of what a neighbor is, right? So you would need some notion of like consecutiveness. So as long as you could map them to the integers, this would work. Let me think. This might be, yeah. And then you could also do this in terms of like, if you needed to pair the data in some way. So as long as the objects you're looking at have some, piece of data, some data member that is consecutivable, I guess. Yeah, it's something you could do. Okay, anyway, so 20, we look to the left, we look to the right, no neighbors. So we pick another random element, just for the sake of demonstration. I'm going to say, oh, it gave us 10, that's crazy. So we have 10, that's one element. We say, is 9 somewhere in the set? No, it's not. Is 11 somewhere in the set? No, it's not. So we know we're done with the left neighbors and the right neighbors. Okay, and then finally we would say, again, arbitrarily, I'm going to say, hey, it gave us 4. Is its left neighbor here? Oh, yes, it is. Okay, so 4, there's one element. And then we'll go left. 3 is here, that's 2 elements. And then we'll keep asking that same question with the new target. Hey, is 2 here? Yes, it is. There's 3 elements. I don't know why I'm writing these, actually. Ignore that. Okay. And then we would ask ourselves, hey, is 1 here? And no, it's not. So that means we're done with all the left neighbors, right? Now we can go on the other side. Okay, when we started, our target was 4. Is 5 here? Yes, it is. Okay, and then is 6 here? No, it's not. So now we're done with this neighborhood, and the elements are 2, 3, 4, 5, and the length is 4. And so obviously out of the options we got, this is going to be our longest one. Okay. Any questions on the approach here at all? Any comments? I I don't know. I keep saying song recommendations. You guys have given some good ones, but let's go ahead and jump into the code then. If you have a question, please throw it in the chat, but let's get to the solution here. Okay, so we're still going to want this maxlen over here. What I'll say is like num set equals, so this is a quick way to produce a set out of a list. We just set and we give nums as the argument. Okay, and then I'll say while, so we want to look through all of the elements in the set, right? So I'll say while num set, and this will continue as long as there's anything in the set. Let's see. I'll say current element. Well, I'll just say current because there's no like notion of indexes in the array anyway. So I'll say current equals numset.pop. Okay. We also need to track what the current length is. So I'll say current len equals 0. The current element is numset.pop. So this gets us, again, just some arbitrary element in the array. And I'll say while, I'll say numset.remove. Oh, so sorry, I actually don't need to do this. This is what I was going to write, but pop actually removes the element and gives it to us. So we don't need to do this. So by the time we've done pop, we have some arbitrary element and it's been removed from the set. Okay. In fact, what I'll do is I'll actually set current length to 1, because if we're looking at an element, we definitely have a length of 1 in that sequence so far, right? Okay, and here's what I'll say is while, yeah, I'll say left target and right target are going to be current -1 and current +1. Okay, so this is going to track which left neighbor we're looking for right now. Okay, and then now we'll have 2 loops. I'll say while left target is in numset, we've found a left neighbor. We can increase the current length by 1. And we can also, so this time we will remove that element. And again, for sets, this is actually really cheap. It's O of 1 time complexity, so very easy for us to do this. And then now we're looking for a neighbor who is even 1 more to the left, right? So now we can say the left target should decrease by 1. Okay, so this is saying we found a left neighbor, remove it from the set so that we don't have to solve the subproblem, and then now we're looking for the next neighbor to the left, right? Eventually we stop finding left neighbors and then we exit this loop. So this is gonna give us all the left neighbors. And then we can do the same thing while right target in numset. So it's the same thing, just going to the right. If we find 1, increase the current length by 1, remove the neighbor we just looked at, and then increase right target by 1. Okay, and then at the very end of this, when we found all of the neighbors, we've got the length of the entire sequence that we're looking at. We can say, and actually I'm going to show a little trick here, max length should be whichever one is bigger, the current max length or the current length that we're looking at. Okay, and then I think that's it. I think we can just return max len. All right, let's see if it worked. Okay, and then let's also talk about something I did badly here. No comments whatsoever. This isn't the worst because hopefully your code is somewhat self-documenting. You have variables that like are representative of the thing that they mean. But it's a good idea to leave some structural comments to say, here's what we're doing in this section. Pretty straightforward for this one, so it's not a huge deal, but you know, it's good practice to be in. Okay, and then this is actually O of n overall. We just have to look at each number once, basically. We do constant time operations when we find a number, and we don't have to solve any subproblems repeatedly, so great in terms of time complexity. The only extra space we need is setting up the set at the beginning, and then some numerical variables. Those are negligible. So yeah. Any questions? Anybody? Great. Well, we'll call it there then. I hope you guys have a great weekend. And we'll post, I think all of the recordings of everything we've done will be posted today. I think we'll have enough, like, YouTube will let us post all those videos. Let me think. Anything else for me to say? Yeah, we'll be back at it Monday. We're going to be looking at two-pointer, I believe, which are some very fun problems once you get the hang of the algorithm. And I will hopefully see y'all then. Have a good night.